Hello students, I am Rashmi Badwa, Assistant Professor of Science and Institute of Technology and Management, Gurgaon from ETCE department. In this video, I am going to discuss with Gautal Algo and chip transform. This is your remaining topics from the unit 1. I completed second unit, third unit and fourth unit, and there are the few topics which are left from unit 1. So I'm completing in this or previous videos the in topics of unit 1. Now student, what do you mean by Gautal algo and chip transform? Basically, when we are doing the fast Fourier transform, that is FFT, so various points have gained considerable property, that is careful selection of the appropriate algo for computing the DFT in practice. Need not to be limited to choosing between this so-called fast implementation, where we will therefore focus in this lecture two other techniques for computing the DFT, that is Gautal algo and chip transform. So what do you mean by Gautal algo? Before starting the Gautal algo, I am re- uh, giving you review of about the previous lecture, that is FFT, DFT, 8-point DFT, 4-point DFT, Radix 4, Radix 2. So when a given signal xn with a correspondingly 8-point DFT xk, what is the most efficient way in the term of total multiplication required to compute that x5 from xn? So you know the हमने बटरफ्लाई वाले वो क्वेश्चंस किए थे डीएफटी एंड एफएफटी, जिसमें हमने रेडिक्स टू एफ वो रेडिक्स टू और रेडिक्स फोर यूज करके उन एल्गोज को यूज करके x5 अप टू x0 to x7 कैलकुलेट किया था by using the formula n log n. So then there we are using the Radix 2 FFT algo. It not the best choice. Judicious application of the canonical DFT equation is enough to beat it. So computing x5 required roughly, yes, 8 log 8, that is your 24, and complex multiplications. And when employing a Radix 2 FFT, Radix 2 FFT algo, since xk for k is equals to 0 to 1 up to 7 must first be computed. However, calculating x5 is equals to summation n is 0 to 7, xn is equals to xn into e raised to power minus j 2 pi by n hota hai capital, which is here 8 into 5n, using this equation. That is OSB is a book's name. I'm referring this book for this topic. Offrin Stuck Buck book is required. Only 8 complex multiplications are slightly simple compared to the Radix 2 FFT or algo, and this example is given in the book, so go through this book. And the FFT algo may be useful for a wide class of problems. They are by no means the most efficient choice in all the situation. सो गॉटल एल्गोरिदम क्या है, छोटा सा है, 5 मार्क्स के दोनों टॉपिक्स हैं या 10 मार्क्स 7 मार्क्स में, गॉटल एंड चिप ट्रांसफॉर्म. The Gautal algo, an efficient method for computing xk for a given k. The derivation of the algo, which is developed in OSB, begins by noting that DFT can be formulated in terms of convolution. Xk is equals to n0 to n minus 1 xn wn n की power nk, that is your twiddle factor, which we done in DFT and FFT. Omega and wn, that is omega n is value is e raised to power minus j 2 pi by n into nk, and when using the n minus k, then its value is omega minus kn is equals to 1. So summation r is equals to 0 to n minus 1 x r wn minus k n minus r. There is convolution of both the terms, and you will get xn convolution of omega n minus nk un at n is equals to capital N. Specifically processing a signal xn through an LTI filter. LTI is a linear time invariant filter with impulse response Hn is equals to Wn minus Nk omega n Un, and evaluating the result Ykn at n is equals to n will give the corresponding endpoint DFT coefficient. So Yk is equals to xk is equals to yk into n. The LTI filtering process is this one. When having a xn and function ka transfer function hn is equals to omega n minus nk u n, then you will get yn, which is equals to the convolution of n xn and hn, and hn is your this one. And by representing the filter by using its state transform, then the transform apply, then xn going through a z transform, you will get the ykn, and having the function inside this z transform is omega n minus mk, that into z ki power minus m. This is representing the z transform of this signal. And since hz is equals to, you know this formula that कि आपका यहाँ पर hz क्या है, m0 से लेके infinity omega n minus m के z की power minus m. So apply the 1 minus AR formula and summation, then you will get this formula. Open this summation, and summation m0 to infinity omega n minus m k z की power minus m is equals to 0 to infinity omega n minus m plus 1 kz minus m plus 1 upon में 1 minus a into r1. So you, after solving this, you will get this equation, and the filtering operation can equivalently performed by the system, that is xn goes to this and you will get the yn. So this is associated with the flow graph. So hz is equals to 1 upon में omega n minus k z inverse. When you are rationalizing is this, and you will get this equation, the filtering operation can equally performed by this equation. Since only evaluating the output of this filter at ykn, the multiplier minus wnk needed only be used at time n is equals to n. With this in mind, the algo requires n real multiplications and a single complex multiplication to compute xk for a given k. This compares favorably to n complex multiplications by the conical DFT equation, and approximately n into log n to n log n complex multiplication are required by the radix 2 FFT algo when computing xk for a given k. A final note about the Gortel algo, since it is not restricted to computing this one for integer value of k, and the algo has a convenient property that can be efficiently computed x ej omega for an arbitrary choice of omega. Basically, this is a Gortel algo is a short topic or a short note of जो कि पेपर में बहुत रेयरली आता है, ज़्यादा नहीं पूछा जाता. Just use in the DFT and FFT computations. Now come to the chip transform algo. This chip transform algo computes x ej omega for uniformly spaced sample omega anywhere along the unit circle. So the algo computes this one, x e j omega naught plus k delta omega, that is equals to summation n 0 to n minus 1 xn e raised to power this was function. So k is equals to 0 1 up to m minus 1, or equivalently k x e raised to power j omega k is equals to summation this one, where omega k is equals to omega 0 plus k into delta omega, and defining omega is equals to e raised to power minus j delta omega. This becomes x e j omega k is equals to n0 n minus 1 e raised to power minus j omega not n w n k xn e raised to power, when we are opening this by formula, and then you will get the convolution of omega square and omega n square by 2. So multiply omega square n by 2 से divide, तो उसकी power minus में यहाँ आ गई. So we are defining this term, this inside the term, whole term is called gn. This e raised to power minus j omega not n omega n square upon में 2 xn is your gn. The above equation is equivalently represented in this equation. So the system is not the reliable as is, since it can neither be causal or stable. If, however, we restrict ourselves to operating on the finite length causal signal xn, the system can be implemented. Since we are also only interested its output yn over a given finite time interval, there are the several possible causal realization of this, and each case the implementation relies on appropriate bookkeeping. There may also some questions on implementing this in the book, and as long as the frequency sampling spacing delta omega is fixed, the system can therefore be easily adjusted to compute for frequency sample beginning at that point on the unit circle. Another advantage of this technique is compute DTFT samples using a fixed convolution block, a property which is convenient when using discrete time analog hardware such as CCD charge coupled devices. So up to this, the two algos, that is Gottel and chip algo, chip jet transform is covered in this video. if 5 नंबर में से ज़्यादा नहीं आता, शॉर्ट नोट ही आता है, इन पर अगर आता है तो बहुत, और ये रेयर पूछने जाने वाला क्वेश्चन, ठीक है। ओके, थैंक यू स्टूडेंट्स, थैंक यू।